All right, so let's talk about propositional logic. And logic is one of those things that a lot of what we're going to talk about is going to seem obvious. It's going to make sense. And there's two things to keep in mind with that. One, sometimes the things that seem obvious and make sense aren't actually true, right? And that is a slippery slope, because I know people who know all kinds of things as being true that actually aren't knowable to be true. They become opinions, or they become things that haven't been analyzed deeply enough. And number two, if we follow a logical train of thought and each step is obvious from the previous one, that doesn't mean that at the end we're going to be at some point that's obvious looking from the beginning. Okay, and that's sort of the power of propositional calculus, is you can start with something that you know is true or believe or assume is true, and each step is like, yeah, that's clear, that's clear, that's clear. When you get to the end and it's like, whoa, how did we do this? Right, we just proved that ducks are actually dinosaurs. And that's part of the power of propositional logic, is being able to demonstrate to a reasonable person, meaning somebody who understands propositional logic, okay, that your conclusion is true by laying down a series of steps. So a big part of what we're doing in this unit is learning how to present these arguments logically, okay? And when I say to a reasonable person who understands propositional logic, what I mean is we're going to learn the rules of propositional logic, for example, De Morgan's theorem, and we're going to be allowed to use that in a proof without having to convince the reader that De Morgan's theorem is true, okay? So we're going to have sort of a set of axioms, if you like. They're actually just theorems, but a set of tools that we can use with confidence that the imagined reader of this, which is usually me, believes these tools work. So when you say, you know, adjacency theorem, I'm going to say, okay, yeah. And I'm not going to suddenly say, well, I don't know if the adjacency theorem always works. Okay, so we'll talk about what these building blocks are, and you'll name them on the side of your proof. And then what you're supplying to the proof is, where should we go from this step? Which of our tools, which of our theorems should we use to write the next statement? And you'll write a next statement, and you'll convince the reader that that follows from the stuff before, because everything up to here you agreed with, and all I've done here is apply this principle that you've already said you believe in, because, you know, this is propositional logic and you believe it. So that's going to be the nature of what we're doing. And the trick is usually not, so for example, we'll prove if a number is even, then its square is even. Well, it probably takes a few seconds of thought to try a few numbers. 2 squared is 4, 6 squared is 36, to convince yourself that that's true, right? But how would you prove it? There's no axiom of math that we're asked to believe that says the square of an even number is even. So how do we convince somebody of that using the axioms that they do accept? So we're going to be working on proofs of things that we can just shrug our shoulders and say, clearly that's true, okay? And the trick is not, you know, saying this is true. The trick is proving it. So we need some machinery before we do this. And this is the machinery of propositional logic or propositional calculus. So here's the most important definition in this entire unit. And I'm flashing this important because we're going to have to come back to this over and over. And a lot of times when I'm grading your proofs and I see a problem, it will be because you forgot this one thing. Okay, so this is the definition of a proposition. A proposition is a declarative statement that is either true or false. And when we write proofs, every statement we write is going to be a proposition. And if you write something that's not a proposition, you no longer have a valid proof. So for example, things that are propositions. I am Nick. That's a proposition. It's a declaration, and it has a truth value. I am Sally. That's a proposition. It's a declarative statement. It has a truth value. 1 + 1 = 15. That's a proposition. It happens to be a false statement, but that doesn't matter. As long as it's a declarative statement, it's making a declaration, this is equal to that, and it has a truth value. So that's a proposition. Things that are not propositions. Go home. It's a statement, it does not have a truth value. So it's not a proposition. X squared plus 2x plus 1. That's not a proposition. It's an algebraic equation, but it's not making a declaration. What would be a proposition is the following. X squared plus 2x plus 1 equals x plus 1 times x plus 1. That's a declaration, and it has a truth value, and it happens to be true. But this, not a proposition. And if this is a line of your proof is no longer a valid proof. If this is a line of your proof is still valid. That might not help you with what you're trying to do, or it might be the key to what you're trying to do, but it doesn't invalidate your proof to write this because it's a proposition. But this, not a proposition. All right, so you got the idea of a proposition? Okay, and I'll keep hitting that point as we go through this stuff, and we'll use propositions a lot. A propositional variable is usually a letter. It could be more than one letter or a subscript, but we'll just think of it as a letter that represents a proposition. Or a prop. So we can say things like, let X be the proposition. Today is Friday. So X is a symbol that means this declarative statement, today is Friday. And we want to work mostly with these propositional variables because they're easier to write and manipulate than the big long sentences spelled out.
Now in mathematics, a variable x represents an unknown that we don't know. Could assume numerous values.
Right.
Is that not the way you're going to use this here, or is it?
We could change the value of x and have it be another proposition, but usually we won't in our proofs. We're just going to use it as a drop-in replacement for a proposition as opposed to an unknown or a classic variable. Yeah, it's just a notation.
Okay.
So we could also write, let y be the proposition x squared plus 2x plus 1 equals y squared equals z squared. Where presumably we've talked about x and z earlier in the proof, right? So y is this proposition. And we could write that as let y be the proposition. Let me show you what I don't want you to write. And this is the second most common problem in writing formal proofs. So
you say that last one was a proposition that doesn't appear to me that that's either true or false.
Assuming that x and z have some value. So I'm assuming there's some stuff that came before this. So don't write this. x equals today is Friday. Okay, the way I'd like you to write this is let x be the proposition, colon, today is Friday. It's tempting to just say x equals today is Friday. Well, that's a little bit nebulous, right? But here's where you get into trouble. If you try to do that with the second proposition, what do you end up writing? Y equals x squared plus 2x plus 1 equals z squared. Well, this means something very peculiar to us. This means y is equal to x squared plus 2x plus 1. And it's also equal to z squared. And now when you start trying to use y in other propositional statements, it's no longer a proposition. So if you mean y is the proposition that this is equal to that, make sure you write it out like this. Let y be the proposition, x squared plus 2x plus 1 equals z squared. And it's just because we're using equations that include equalities a lot in our proofs, and if we use an equal sign to mean this is a proposition equal to this English sentence that follows, right, the notation gets ambiguous, and inevitably it trips people up. Because it's somewhere along the way they start using y as a mathematical variable. So stick to the full language. All right, so put a big X through that. Don't do that. So we use the symbols T and F for truth values. T is a synonym for true, F is a synonym for false. All right, so with that set of machinery, what we can do is the same thing we did with sets. We can start creating new propositions from old propositions. This is what we like to do. So how old do you think this subject is? This idea of propositional logic or propositional calculus.
About 2,000 years.
Yeah. So George Boole, 1850s, right, came up with what we call Boolean algebra. That was much later in the game. Aristotle was actually playing around with this stuff around 300 BC. So this is old stuff. All right, so how do we generate new propositions from old? Well, this is going to look familiar again. So one thing we can do is what we call negation. And negation we have a funny symbol for. It's a horizontal bar with a little vertical hook on the end. And we can apply that to the proposition. And this is called the negation of P, or sometimes it's called not P. And so if P is the proposition that I am Nick, not P is the proposition I am not Nick. Technically it's not I am Nick, but if we were to put it in English, I am not Nick. If this is the proposition Q, 1 plus 1 equals 15, then not Q says 1 plus 1 is not equal to 15. So it just negates it. And we can write a truth table to describe what negation does. If P is any proposition, it's got a truth value of either false or true, because that's what propositions do. And the negation of P will be another proposition, but it has the complementary truth value. And that looks like a good old 7404 inverter, right? Or a not statement, or a complement of sets. So throughout all of this, let P and Q be propositions. So we can write P in a caret and a Q, and we can call this the conjunction of P and Q. And we can describe conjunction with a truth table. And there's only 4 possibilities for the truth values of P and Q. And the conjunction is a new proposition which is true exactly when both of the propositions P and Q are also true. And we can think of this as an AND. So let's suppose this is P. Well, let me put these up here. Let's suppose P is the proposition that I am Sally, and Q is the proposition that 1 plus 1 equals 15. Well, P and Q is the proposition I am Sally and 1 plus 1 equals 15. It's another declarative statement. And you can see that if either of these statements is false, then the AND of them is also going to be false. Let me name this one R, so we can talk about that. Okay, there's another operation which is written by a wedge, or an upside down caret P or Q, and that's called the disjunction. And that's also an OR. And we can write a truth table for that. And the OR is true if either or both of the propositions are themselves true. So P or Q would be I am Sally or 1 plus 1 equals 15. Well, that's false, because both of those propositions are false. But R or P, right, the disjunction of R and P, would say I am Nick or I am Sally. Well, that's a true proposition. Turns out the first one is always true and the second one's always first. But in any possible case, at least one of those is true, right? So true and false. Turns out the disjunction is true. And something to keep in mind, this OR is sometimes what we call an inclusive OR. Because note, if both propositions are true, then the inclusive OR is also true. So today is Wednesday, or it's cloudy outside. The truth value of that is absolutely true. Because today is Wednesday, and it's also cloudy outside. Right? So certainly the OR is true. But in English, sometimes OR actually means an exclusive OR. Right? Soup or salad, you don't usually get to pick both, unless you pay extra. I'm either going to do my homework or I'm going to watch TV. Kind of implies you're not going to do both, right? But logically, an OR doesn't mean that you've got to do one and not the other. So if you're doing both, you could still say, yeah, I'm doing my homework or I'm watching TV. But sometimes we talk about the exclusive OR. Which we write like in 250. And the exclusive OR fails to be true if both P and Q are true. That doesn't come up very often. So some of the homework questions deal with taking statements and writing them in this language of propositional calculus. So let's look at some of the questions from chapter 3. So let D be the statement, I like discrete structures, C is I will pass the course, S is I will do my assignments. Express the following propositions in symbolic form. I like discrete structures and I will pass the course. So how would we write that using this formal language we've been developing? I like discrete structures and I will pass the course.
D caret C.
Yeah, it's a conjunction of D and C. So we could write that as D caret C. That's not exactly the same thing as C caret D. We know that A and B is the same truth value as B and A, but technically if we want to convert this sentence into propositional language, this is the proposition D, this is the proposition C, this whole thing is D ANDed with C. So you would want to write it as D caret C. I will do my assignments or I will not pass the course. What would that look like?
S wedge, not C.
Everybody agree with that? All right, I will do my assignments as S. I will pass the course as C, so not C says I will not pass the course. So S or not C. So wedge or V. And you can put in parentheses if you want to sort of keep things logically separate from one another. Parentheses don't do any harm. And they can help clarify. Right, so you got the idea of that? So the other thing that you can do is given a set of propositions, you can try to interpret what these statements mean. For example, not P or Q. Well, P is the proposition 2 is less than 5, and they use the dreaded P equals notation here. Don't do that. Okay, I would have a talking to the author about this. P is the proposition 2 is less than 5. Q is the proposition 8 is an even integer. So not P or Q, how would we write that in English? Yeah. Yep, not P becomes 2 is not less than 5, or we might say 2 is greater than or equal to 5, or, and then Q is a statement, 8 is an even integer. So we could write 2 is bigger than or equal to 5, or 8 is an even integer. So sometimes we're going one way, sometimes we're going the other. And those are some homework questions to work on, so questions 2 and 4 are the same thing. I didn't give you number 4, that's fine, okay. All right, so we can construct more complex truth tables, right? So let's look at S or not C. Well, if you want to make a truth table for that, list all the possible combinations of truth values for your variables. And then just like in 250, work systematically. Don't just try in your head to take S and OR it with not C. Put a separate column in here, show what not C is equal to. So if C is false, this is going to be true, and if C is true, this is going to be false. And now find the disjunction of S with the negation of C. So just take these two columns and do the logical OR on them. So true, false, true, true. And if you do this in steps, you got two advantages. One, you only have to do one operation in your head at a time. You've always got two columns of things and you're just doing a simple OR or an AND or an XOR or something. And two, if something goes wrong, there's a chance I can figure out where it was and I can tell that you actually understood what you were doing and you just made a typo somewhere, right? So if you accidentally put a false down here, but this was filled in correctly from that, you get most of the credit. And so there's some questions you can work on in the homework for constructing truth tables. And remember, if you have two variables, there's 4 combinations of truth values. If you have 3 variables, there's 8 combinations of truth values. If you have 4 variables, there's 2 to the 4th, 16 combinations of truth values. Right, so that's going to be almost a whole page for ones like F down here. All right, so let's talk about implications. So this is another way we can create new propositions from old, and this is probably the main way that we're going to deal with propositions in here. Now, we're going to be using conjunction, disjunction all the time, but most of the problems that we develop in this course are going to deal with implications, or what we can think of as a conditional statement. And this is where Boolean algebra, propositional calculus starts to get into the interesting stuff, because people were trying to figure out how our brains work, basically. How do we think? How do we reason, right? And they were trying to sort of put this on a rigorous kind of mathematical foundation, and that's where a lot of this came from. And so a big part of that is being able to deal with conditional statements. So a classic conditional statement: if something P, then something else Q. Where P and Q are propositions, and I won't keep writing that, but P and Q are propositions. So if today is Wednesday, then we have discrete structures at 2 or at 12:30. So if P, then Q, and we have a shorthand for this. It's just P, arrow, Q. So this is a shorthand for if P, then Q. And P is what we call the hypothesis, and Q is what we call the conclusion. So for example, let P be the proposition, today is Wednesday. Let Q be the proposition, we have 2:15 today. So P arrow Q is a new proposition which says if today is Wednesday, then we have 2:15 today. And barring the oddities of English, you can pretty much just take an if, put it in front of whatever P says, then take the word then, put it in front of whatever Q says, and you've got a new proposition. Now, this is not saying that today is Wednesday. It's not saying that we have class today. It's saying if today is Wednesday, then we have class today. Right? If I win the lottery, I will wear a new hat tomorrow. Doesn't mean I'm going to win the lottery. Okay, but if this happens, then that happens. And there's other ways that we can say this. We can say things like if P, comma Q. I don't like that one. That seems ambiguous, but you'll see that written sometimes. We can also say P is sufficient for Q.
Can we say P implies Q?
We can say P implies Q. We can also say, and this is an odd one, Q is necessary for P. And that's a little weird. It's necessary for today to be, it's necessary that we have 2:15 today in order for it to be Wednesday. Okay? We're not implying causality. We're not saying if we cancel class, the day of the week will change. Okay? We're saying that since if today is Wednesday, we have class, it's got to be the case that we've got class today in order for it to be Wednesday. So that can be a little wiggly. We can say Q follows from P. We can say P only if Q. A sufficient condition for Q is P. There's all kinds of equivalent forms. All right, so we'll stick with these propositions. P says today is Wednesday. Q says we have 2:15 today. So if you start with a proposition, if P then Q, we can derive other propositions from this one. One thing we can do is we can say if Q, then P. If we have 2:15 today, then today is Wednesday. So this is called the converse of this original statement. We can also say if not P, then not Q. That's called the inverse. This says if today is not Wednesday, then we do not have class today. And we can put those together and make something called the contrapositive, not Q. If not Q, then not P. All right, so P, today is Wednesday. Q says today we have 2:15 today. We're assuming that this is a true proposition. If today is Wednesday, then we have 2:15 today. And that is true, right? So what does the converse say? It says if we have 2:15 today, then today is Wednesday. Is that a true proposition or a false one? If we have 2:15 today, today is Wednesday. Is that always true? It's not true on Mondays or Fridays. So even though this original proposition was true, in this case the converse is not true, it's false. How about the inverse? If today is not Wednesday, we do not have 2:15 today. That's not true either, because Monday's not Wednesday, but we do have 2:15. So the inverse might also be false, even though the original was true. But the contrapositive is going to be true. If we do not have 2:15 today, then today is not Wednesday. That's actually always true. If we do not have 2:15 today, then today is not Wednesday. And if you just think about our schedule, that is a true statement. Because if it was Wednesday, we would have 2:15 today, because that's what this original statement said. So it turns out the contrapositive is logically equivalent to the original statement. The converse and inverse are not. And this is one of these places where you get into all kinds of misuses of logic. Right? So simple one. If you rob a bank, then you own a gun. If you own a gun, then you rob banks. Does not follow logically. But that simple difference eludes people. So we'll see lots of examples where we'll construct different versions of a conditional statement, and we'll have to keep in mind whether what we're doing is logically equivalent or not. The contrapositive is always going to come to our rescue, though, right? That's going to be logically equivalent to this. And sometimes it's a whole lot easier to prove the contrapositive of something than to prove the original. And once we've proven the contrapositive, we can say, therefore, this thing is true, because this is the contrapositive of that. But if we prove the converse, we haven't proven the original. And this is the third most common mistake we'll see in proofs, is you'll end up proving the converse or the inverse of the original statement, and you can't conclude the original conditional from that. All right, I think that gives you enough to do all of the homework. If I missed something, if you don't have enough to do all of these questions in section 3.3, don't worry about it, okay? We'll talk about them, but definitely try to do the ones from 1.5 and 3.1, 3.2. All right, and we'll keep developing propositional logic on Friday, and we'll also play around with some infinities. All right, so I'll see you next time.